Hi, welcome to the next part of the video series. In the last part, we've compiled, we included into our Quartus project a bit more comprehensive signal analyzer to do some more deep dive analysis on the signals and why our mmap instructions to the kernel do not work. And in this part, we will dive a bit more into the system. I've started the compilation process on Quartus. In the meantime, I did some research, and there is one line here, which is the strict devmem, which means the access to certain parts of the memory is not allowed from the user space. And this guy here, which is in our Linux kernel configuration.config file, which we created using makefile, and this line might prevent that we cannot access it, and we cannot see here some instructions because we get the bus error message. And now let me start the Linux, and I will show what happens if we do devmem, and then we can think of what we should do next. But first, let me start the Linux. 1 second. Good. Let us directly do it using SignalTap, because I've already modified the top HBS QPF file, and we can program the first stage bootloader of the FPGA, then boot the Linux, then I will show the instructions, and then we can start playing around with that. What we can do, I guess, to fix that issue is building a Linux device driver. And if we have that device driver in the kernel, we could access the specific regions. This is at least what I think. But before doing that, I figured out something really interesting. I will enable some LEDs on that board, and I will show the LEDs and the device tree file, how that works. But first, let us scan the chain. Now this is our device. We've already configured that. Let's do the programming. I hope this works. Last time I had some issues. Yeah, it worked because now we can see the ARM core side. Good. Now let us start SSH. I have some resolution issues. Okay, it takes a while until it boots. Now, good. I have the console. That's good. Let me. Now I made the video quality a bit better. Now it should be better. A bit slower maybe, but a bit better. That's okay. Good. Our Linux works. That's good. Now let me show you something. Good. Let us change to the folder. Let us take English keyboards, system plus let's okay. Okay. Now let us change to the let's folder. Now let us take FPGA let 1 blue. And what I will do now, I will turn on the camera and point it to the board. 1 second. Okay, now let's do something else. Let's start cheese. I guess LED 2 is better. Blue, echo 1 into brightness. Okay, that's the wrong LED, but we can see it at the very bottom. Let's do CD FPGA LED 0 blue, and now echo. Yeah, now we can see the LED, the right one, and we can turn it off. We can do also I don't know how to write heartbeat. Heartbeat. No. Echo, heartbeat, and brightness. Okay. How did that work? Okay, it should be like this. Should pipe it to the trigger. Now we can see the heartbeat of the device. Okay, good. This is now nice. But now we should ask ourselves the question, great, but how is this LED mapped to the kernel? And understanding, like I saw this before, so I wanted to debug how why I cannot access the specific memory region. And then I figured out, okay, we have the peripherals in our Quartus design, you saw them, and how about controlling them? Then we can start the on-chip scope, what I will do now. And then hopefully we can see what is going on. It is already programmed. JTAG communication error. Okay. Now it's ready. Now this guy is not compatible. Oh yeah, not compatible because I didn't do the patching. Okay, that's my fault. Let's do the patching project. This guy, patch bitstream. We take this guy and create this guy. Good. Let's do it. As a patch. Good. Now it should work. should work. We should trigger this time. Okay. No. Okay, now I had to restart the compile process. Okay, that's good. What I will do now is I would like to dive a bit deeper into the LED thing. Let's start a terminal, SSH into our device. Okay, now let us see what happens here. First of all, let's change into our project file folder, and here let us try to understand our compile flow. What we first do is we first set up our stuff, build the trusted firmware, then we configure U-boot for the Agilex 5. We do a patch. Okay. Here we do the binary to Intel hex format conversion. New build scripts. Here we build our Linux kernel. We cd into this folder and we execute make. Good. And we build the device tree blob. This is the device tree blob. This is our friends. FPGA-0 LED. Red, green, blue. The label is this one. Use the GPIO LED PO0. LED PO0 is here. This is the address of that guy. Is that right? I guess so. the LED PIO0, this is parallel in out, 0, is at this physical address. This guy is the basis address of that register. I don't know why we have an 8 here. This is the size of the register. This thing is compatible with this driver. I guess this is already the pre-offered driver which is already available in the kernel. Let us see. Physical base address. The length of the microcontroller's registers. What do we have here? Our physical base address is it this guy or this guy? What? I guess this is the physical base address. What is this? Let me open Quartus. Now let's start this guy and then start this guy. Yeah, that's the hardware address. What is then? Let's see this guy. Okay, now let's continue with our analysis on the device tree file. Quartus in the meantime compiled. I stopped the video, my recording yesterday, and now I'm continuing with the work. Later we will compile this, include our first stage bootloader into it and then start our Agilex 5 board with that. But before starting with this, I would like to analyze a bit more this device tree files we have here. This is where I stopped yesterday. One thing I would like to understand now is what the meaning of this guy is and why we have here two different addresses and how to understand this. What I guess is this is the base address and this indicates the offset to the base address, which is indicated here. This is my guess, but we will find this out. Okay, after a bit research, I have some more information. Here we see the SoC definition, and here we can see the mappings. So the device which the HPS sees on 28000 is actually at 0800, and this is the width, which is 1 byte of that range. And here we say in the device tree the physical address 0800, which is here. Let us see our address map. Let us zoom out, system view, zoom out, address map. Here the peripheral at 08, this is the real address. And here we tell our device tree, hey listen, this is the real address, like here, but you will see it as this. And if you now scroll a bit down, this is the definition of the bridge. And if we now scroll a bit down, we can see, okay, this LED is at 0800. Actually, I think this guy should be also a 2. I don't understand why it is a 1. I will do a bit more research on that. But now we understand it a bit better, I guess. Yeah. And let me show an example. This is something I did. For example, we can now turn on the LED, this 03, which is this guy, LED 0. We can do a red one. And now let me open Cheese to show you the camera. Okay, the camera is turned off. I will turn on the camera. I will open the laptop. 1 second. Okay, now the camera is working, and now let's see what will happen. Yeah, now we've used the same LED, but we've made it red. And if we write 0 into it, it should be yellow. Yes. And 1 is something else. Oh, that's great. And this is the system ID at this address for the HPS, but in reality it is this guy here. Great, now we have understood this as well. Regarding the LED driver in sys class, let me cd into that. Sys class LEDs. These LED drivers are already generic LED drivers. We have to enable them if we build our kernel, and we can use them without any problems. And yeah, basically now we've a bit better understood how the device tree works and how the mappings are done. And now let us continue with our Quartus project and try to see really on the bus how we write and read to that specific addresses. Here must be our SignalTap logic analyzer. Let us program this guy. Oh, it will not work. Yes, because we need to do something. I will close this. I will close this as well. No, I will open it like this. Okay. What I will do here is I will cd into projects 2, and then I will execute patch bitstream. Now what is going to happen is the newest bitstream I've compiled, I'm going to patch it, and with the U-boot SPL, and then I should save it into the right location. Let us see if it is in the right location. It is. The folder is going reference design output files ls. Let me change to the English keyboard. That's better. Here it is. What I can also do here is grab top. Oh, HPS is better. Yeah, I can see it now. Ah, here. This is our friend. Good. Now we will start this guy again. Scan chain. Now once the programming is done, the LED should stop blinking because the Linux should restart. Let's see if it will work. Yeah. Acquisition is in process. Okay, SSH. Great. Acquisition is in process. devman2. Right. No, devman2 0x. Oh, let me copy read address. Devmem2. I can write this. What did you write? Okay, devmem2. Write this into the But actually this guy should work. I should be able to see this here. Strange. Really, really, really strange. Okay, it sees it. Yeah, this is my 7. But why it doesn't stop the recording and show it to me? Run analysis, auto run analysis, read data. I would like to run analysis for a trigger. Okay, I can see it here, but still, I don't like that. I don't like that. Okay, now I fixed the issue. I just need to click here and then select either edge, then restart it. Then what I will do is I will write some other number, for example 1. Now the trigger worked, and now I can see I have a yellow LED. For example, with 7 the LED is off, 1 yellow LED, and let me now write a 0 to make the LED off. This triggers the whole thing, and now I can analyze the data. And what I can see now is I really can see the address on the bus is 0800. And but I do devmem on 02800. And this means that really Linux sees this address as 28 something, and in reality it's 08. And we can see this configuration here. Which is actually a nice thing. What I will do is now continue working on the system, and I will stop the recording for now because now we have a bit better understood how the whole mapping and stuff works of the LEDs. I will stop the recording now and continue working on this project in the future. Now we've seen how the mapping works, how the hardware sees the software, and for tonight I would like to use the time and start another compile process, and this time I would like to extend our SignalTap to get even more data into it. And for this I would like to add some further nodes into it. How did I do that in the last thing? Yeah, 1 second. Okay, I just have to double click here. Now what I would like to understand a bit more is, let's open this guy. Oh. View, reset the system layout. Okay, I will close it and open it again. Okay, I would like to understand this guy a bit better, this guy a bit better. Okay. Ah, search. HPS to FPGA. Mhm. Good. Then that's it for today with the recording. Let's compile this and then I will continue working on that project and I will try to understand the whole system a bit better and share my findings with you. Thank you.